Hello everyone, thank you for tuning in again here on AtCoder. Thank you for the positive feedback on the other videos, so you can check out them on my channel on Codeforce's AtCoder. We nearly every week we film something here, screencasted, and yeah, so there was a lot of positive feedback. Thank you so much for just subscribing and stuff like that, because my channel is very small and competitive programming is not something that a lot of people actually do. It's something, I would say, a very niche thing that 99% of programmers even don't understand what it's all about, don't know these algorithms and data structures. And when you train competitive programming, it's very fulfilling, and then you can just boast about your algorithmic knowledge. Okay, so the contest starts. As usual, we are using the CPH judge here. People ask me, what is this? This is the competitive programming helper judge. Very cool extension. I'm using this competitive companion here. I click on this button and the program statement is just parsed. These are the examples here, and here we go. We have 3x3 board. From integers 1 to 9, you are given two integers a and b. Between 1 and 9, determine if the two squares with a and b written on them are adjacent horizontally. So if they are adjacent horizontally, it means that the difference horizontally it means like this. So if they're adjacent horizontally, it means that the difference is 1, but there is these edge cases, so there's a and b. I read a and b in, and then I would say that the okay is if so I will say like this: if a is bigger than b, I will swap a and b, and then b is now bigger than a, so a is equal to b minus 1, and a cannot be either of these, so 3, 6, or 9. So a is not divisible by 3. If that's the case, then so okay, yes, and no. So a cannot be divisible by 3, and the difference should be 1. So this should be judged fairly quickly. We got AC on A. You are given a grid with n rows and n columns. An integer aij is written there. It can be either 0 or 1, so there's a matrix of zeros and ones. Shift the integers written on the outer squares clockwise by 1 square each, and print the resulting the outer squares. So on the outer squares, these integers here, we kind of need to just shift them clockwise by 1. And this is just like implementational task. So vector, I will make a vector of n strings. What I will do is I will go through all of these, or should we just, yeah, we could go through all of these. So There are many ways of doing this. There are maybe it would be just easier just to do this through, so it might be, I don't know what is more educational to be done, but so I will do it like this. So I will say there is some string s. I will go over. So I will go over like that, and then like that, and then like that, and then like that, and create this s string. Then I will shift this s string by 1, and then repeat the same thing. So here I will have 2 repetitions. I don't know if there's probably a better way of doing that, but whatever, doesn't really matter. So I will just say s so there's like this, then there's this, and then there's this, and then there's this. So there's I will copy and paste them just. So the first row and then the ith column s should be added to that. And then, or maybe without this for loop, maybe a little bit more better like this. So the first is added on this, then it's added n-1, so it's added, the I is here, then this is n-1, this is the last column, but we repeat this here, so we kind of need to pop back this, or I will just start from 1 here. Then I would go here and I will say, okay, now we need to start from n-2 to 0. So this is the reversed thing, and this is n-2i, n-1i, so this is the last row. And then you need to start from here, and then this is like this like row and then 0. So I created this s. Now I need to do this again, but this s will be shifted by 1. So I will say rotate as begin as what is, how did we rotate this? I don't remember how did we rotate it. As begin as and as begin plus 1 as end. And then from here it's like a of this is equal to sp plus plus, and then here a of this is equal to sp plus plus. So like I'm just putting it back, and this p will be just like a pointer, and then I will print out the whole matrix. Oh, this is n. I mean, I just need to print out this. Did I shift them wrongly? Wait, if I do this, that should be no shift. Yeah, there's no shift. Is it -1? No, let me just start here at 1, and here I would say this will just say, okay, get actually, like, I don't p plus plus I can add this. So after the iteration, I will just module p with the s size. What is happening here? Yeah, that is correct. Now let me see just the indices. These are the first row. This is the last column. That's correct. Then that is the last last row, and then starting from n-2 till 0, and then starting from n-2 till 1 is this. Oh, so it's on the other side. It's like -1. No, it's not n-1, it's this. Yeah. So that was kind of bad, but whatever. Snook, the doctor, prescribed n kinds of medicine for Takahashi for the next AI days. He has to take BI pills of the ith medicine. He does not have to take any other medicine. Let the day of the prescription be day 1, on or after day 1. When is the first day on which he has to take K pills or less? Okay, we got AC on B. K pills or less. So for n kinds of medicine, for next AI days, he has to take BI pills, the ith medicine. He does not have to take any other medicine. Let the day of the prescription be 1, on and off. So there's this, and then on day 1 he has to take 3, 5, and 9. And 2 pills of the first, second, respect total he has to take. So yeah, So we can just int nk. So for the next, so we could do some binary search, but can we avoid binary search? Just take for the next AI days. I mean, I don't know if we can really avoid binary search here. No, we can't. So I think I will do it with binary search. So for k, so I will search on which day yeah, so like this. So these are what medicine he needs to take. And for the next AI days, he will take this medicine. And I will binary search. I will start at day 1 and end at some day. So the middle point, and then we need to check how many pills still on this day he will take k pills or less. So number of pills do this. Yeah, so we go over all of these, and AI is what days it is. If AI.first is, so this is this day, so bigger or equal to m, pills plus equal AI dot second. If pills is bigger or if it's smaller or equal to k, L is m, else R is m. Or smaller or equal first day, so we need yeah, so I'm searching for the least day. If it's smaller than equal to m, then it means that this is possible. So if it's like bigger than, it means that this is possible. So it means that R is M and then L is M. Now in this case R is a valid choice. That passes. Let me just check this out. Yeah, I think so. That should be fine. Okay, so D. We have an undirected graph with n1 plus n2 vertices and m edges. The following properties are guaranteed. Vertex u and vertex v are connected for all in the n1. So there's like a click in the all n1 vertices. And then they're connected for all of these. So there's another click. The both clicks are vertex 1 and vertex n plus one. These are disconnected. C gets accepted. Consider performing the following operation exactly once. Choose an integer u from the one click here and an integer v from the other click, and add an edge connecting these two. We can show that vertex 1 and vertex are always connected in the resulting graph. So let d be the minimum length number of edges from this path. Find the minimum possible d resulting from adding an appropriate. Find the maximum possible d resulting from adding an appropriate edge. So you want to maximize the distance between vertex 1 and vertex this. So given like 2 clicks. Oh, is that not a click? Vertex n plus 1. Wait, why is that not a click? So n here is 3, and then we have 4 edges. Oh, so yeah, so 4 edges. Okay, the guarantee properties are just connection, are not clicks. So it is guaranteed that there are 2 undirected graphs inside, so 2 undirected components that are connected like this, and we want to maximize this distance from 1 to 7. So we push in this component what is the maximum, like BFS, and we push in this component the maximum. And then you just want to connect some edge, and then if you set, so these 5 maximum possible. So okay, so just fairly simple problem. Sometimes you expect problems to be a lot harder, but they're not. So okay, so like this, vector int. I always do this. And then there's n1, n2, and there is, what is this, m. Of course it's m. So adjacency resize n1 plus n2 for each of the m edges. Adjacency pushback, adjacency pushback u. So just a simple BFS. So this is like the distance, and then I just name it distance many times because for v in adjacency of t, so for each of his companions, if v is if the distance of v is bigger than the distance of t plus 1, distance of v, distance of t plus 1, q dot push v, and then we want to find like maximum distance. And then what we want to find here is just the BFS from 0 plus BFS from n1 plus n2 minus 1. This is like the last component there. And then plus 1 probably because we add an edge there between these two. This edge is added. So now that we are on E and F, these are more serious problems. There's family of consisting of person 1 to person n. For each from the second person, person i's parent is person pi. So there's like a tree. They bought insurance m times. Person xi bought the ith insurance, which covers the person and their descendants for the in the next y generations. This is pretty cool. Okay, D gets accepted. So this is pretty cool. So in the next y generations, it covers this. How many people are covered in the insurance? So the trick here, like, okay, so you have a tree. So you have some tree, and then some here subtrees, but like this person may buy insurance for the next, for these generations up to here, for the next y generations. And then if this person bought insurance for like these generations, it could like cover them here, and plus some generations that are here. This is a more serious problem. Okay, so what do? So when you enter this node, you kind of wanna, so you enter this node, you add his insurance. And you come, when this insurance expires, then like you kind of delete this insurance. And then you go here, you do your own job, but then when you re-enter this node here, you need to enter again the insurance of this guy here. And can I just have like a set of, and then when you exit this guy here, you immediately remove the insurance from like 2 sets. Maybe something like that. So that's a, I would say, really cool problem, because it's innovative in some way. So like instead of M, okay, I will name them Q, so Q insurance, like erase. And then you want J series size M, and then you want for like N minus So this is just adding, creating the tree, and then there's like Q insurances. So this is like the insurance. Each node will have -1 insurance, and then you have node and generations. So for the insurance of the ith node is of course going to be maximized here. This is one thing. And then okay, so we have all these insurances. Then we will have like two sets. One set is like active insurance, and one set removed insurance. And then in the DFS, I will say this. So there should be some answer here. So if active is not empty, then I will add to the answer something. But first I would want to find out I want to find out if insurance at U is not -1, then the active insurance. So in active insurance, I want to store which. So first I need a DFS for what is the depth of each guy, because the depth is, I don't need a DFS, I can just do this depth. I can do this. Okay, so if it's not empty, I need to push into the insurance U, because now it's like U has activated. But they can't be set because I don't want to check all the time. I kind of wanna have like a priority queue or something, which will the greatest depth. Yeah, so like I want some priority queue. Also set can act as a priority queue, but it won't be that fast. Priority queue. There's like it has to be set because I need to delete. Yeah, I need to do it has to be set. So okay, so in the set I insert myself, so I inserted this U because it starts from here. In this set, insert U, then at the end, what I will say when I exit this node, I want to erase you from the active and from the removed set. That's what I want to do at the end when I end this. Now here there will be for each adjacent at you. So okay, so I can't continue in the active to the adjacent node if so active has to have the depth in, right? So it has to be a pair of integers, which so it has to be a pair where this is depth and this is node. And the active is like depth at u plus whatever we insert at u and the node u. This is whatever we insert. So if the insert is 0, then this depth is the same as u. So now when I erase it, I need to erase this. Okay, so this here would be, so while active is not empty and the end of active, so active dot end, so the previous of end of active dot first, so the depth is smaller or actually totally equal to the depth of, or smaller or equal, I would say, right? Yeah, so a smaller or equal to the depth of u. This guy here so this guy has to be put into the removed section, so it has to be, I'm sorry guys, just it has to be added to the removed section. Also from active it has to be erased. Then I go into like DFSV here. Then at the end, all of these that have been removed at this depth. So all of these that have been removed at this depth. Now here is like while all of these that are removed at this depth, I will add them back into active. So just juggle around them. I don't know, is this fast enough though? So why this should be fast enough? Yeah, no, I mean, no, I don't like this. I I don't quite like this due to the fact that like you could have this, you could have a lot of nodes having the same here. When you come to this point, all of these nodes will trigger this event here. I don't quite like this. Can't prove that. I don't think you can prove that this is linear. So if you know like about tree linearization, but here you can't really do tree linearization because you need to stop at some point. So it's all about what is the longest here that you can kind of. So when you come to the next here, what is the longest depth you need to assure for? So this is the idea. What is the longest depth? In longest depth you need to, and it says like, so I don't think I actually need this sets. I will say like this: longest is max of longest and depth at u plus in su. And this here will definitely say, okay, so the longest when I approach this is something there, and then says if longest is bigger or equal than my depth, which answer plus plus, something like that, I would say. Depth is this should be right. Depth, this is from 1 to n. The q things you maximize with q, then longest is whatever the longest meant, and depth plus minus s at u of course. I'm not even calling the DFS function. This apparently works, this apparently doesn't. I will just close down the window. Or not, maybe not. Whatever. We'll see. So 2, yes, that's correct. And then 2, 1, that seems correct. This seems correct. And then 0, so 1, 2, 3. This seems correct. Of course, this is not -1. Yeah, this is not -1 because we don't go, like, the depth is yeah, accounting for that. This is a really cool problem. I like it. Okay, so if there are n boxes, the ith box has the shape of rectangular cuboid with width, height, and depth. Determine if there are two boxes such that one's height, width, and depth are strictly greater than those of the other. After rotating them if necessary. Okay, this is called coordinate bit. So we got accepted on me. This is called coordinate-wise 3D thingy, and the rotation is just swapping them. But I have already implemented this thing here, 3D coordinate-wise stuff, and it's in 3D coordinate domination. This is my implementation of it. So I just copy out this. Here I will just paste it here. I'm like, okay, it says that, so first of all I need to add a few things. Okay, second of all, this counts how many of them are. So I just need to say, okay, in answer domination, I will tell you how this works at the end of the contest. At the end we'll have some place for some time for I will tell you a lot of story about this. So okay, so what's the why is vector undefined? Yeah, using spaces. Yeah. There's a lot of story behind this. Okay, so now it's not only about actually like, so this won't kind of work because it will say no, but now you could like rotate one point and then it will say it doesn't matter the rotation of them, so rotate if necessary. And how do you say this rotated if necessary? Or maybe we should re-implement this, but let me see if I can modify it without re-implementation. Or maybe is like a better way of putting this, and I don't think there is a better way. So first what it does is like it sorts the point by x coordinate, and then it has this frontier, and for each x and y then like does this frontier, and this update function essentially just says, okay, I will add this point right now. While adding this point, it checks if there's some other point that is dominating this point or not. But now the trick here is that, okay, I will add this point, but I can so it's a little bit complicated, but let me see. So the frontier here is added, like it's added in the frontier here. So are they all distinct is my question. These are strictly greater than that. So yeah, so what I can do is I can do all of these points, but I can do them in like all of the various permutations. So let's just do this. So we read the points and then we say, so we read this and then we say do while next permutation and then we say a dot pushback. This is PS order 0, PS order 1, PS order 2, and then this is A. Why pushback doesn't work? Oh yeah, this is point. Okay, this works. I will explain at the end a little bit more about this. Dominations and things. It should be fast enough. Now that we solved through F, okay, there's G. Find the number modulo this of permutations such that the absolute difference between this and its index is greater than x. So there's like, and x is to 5. So this is kind of an interesting simple problem. Okay, we got accepted through F. And this is EX. Simple path counting problem is definitely not a simple counting problem, but I mean, it could be simple enough. I'm not sure. Like, but 10 seconds? Oh no, this is some kind of FFT or something. Oh no, this is just okay, so band permutation. This will try to solve. Find the number. So some permutations where this is bigger than that. So it says that the absolute difference between myself and where, like, this means that if, so let's say there's like some kind of permutation like this, and you know a permutation with like cycles, if it's like that, it means that every number is in the same place. It means it's like 1, 2, 3, 4, 5, 6, 7, 8. But let's assume, so I mean, we want to say that on some number, let's say this, on every number, this arrow doesn't go here, but it goes, if x is 5, the difference is, if x is 3, it can't go to the adjacent this here, so it can't go here, it can't go here, it can't go here, and can't go here. It means that like either can go somewhere which is off this, like that. So for that index, so for that index 5, the 5 number, oh no, actually no, I misunderstood, no. So it's pi minus I, so it's the number here minus the index has to be greater than 5, or I mean the absolute value. So what does that mean? If there's, so here can't be 3, can't be 4, can't be 6, can't be 7, but can't be 5 as well. But yeah, so but can be 2. So yeah, this does mean that. So from 5 you can jump to 2 or to 1. So yeah, that does mean that. Okay. N is relatively small and x is way small, which is very interesting, I would say. Say it's very interesting. There could be no such permutations. There could be a case where no, or there can't be a case. If x is, if n is like 1 and then x is, there is no permutation. So apparently, yeah, there are cases with no possible permutations. Okay, something with inclusion-exclusion or something. I don't know. So I would say that, okay, what are not allowed permutations? Not allowed permutations are for each number to have some here pi to be either 3, 4, 6, or 7 in our case, if x is 2. X is 3. So if x is 3, I think, right? So this value is 3. The unallowed permutations are anything that has here, so okay, so we have some constraints. So essentially what we have is p, if x is 3, p5 cannot be equal to p5 cannot be equal to 3, 4, 5, 6, 7, and this at most, we have at most 10 such constraints. For each element. Okay, we have 10 at most such constraints. Now we need to construct permutations such that these constraints are valid. Okay. It kind of looks like some but these are not like very these are not very general constraints. They're very limited. Still, I would want to see here number of permutations with given constraints. I mean, yeah, so with mathematics we can write this. All permutations with 5 for some given permit. Can it be just dp? Can it be just dp? From 5 to also there's like one in the front here. read EX. So you're given two integer sequences. Find the sum of the numbers of the answers to the following question for ij pairs. So you pick one number from here, one number from here, and initially a piece is placed on the first row. How many passes does it take to place to the nth row? It's on bj. If you can move to left, to down, and to right, down. So okay, so for pair A and B, what is the answer? So to some function A and B, what is the answer? The answer would be this polynomial. The answer on how many ways are there would be x minus 1 plus x plus 1 plus x to the nth power. So this polynomial, and take this polynomial and then find the coefficient at index b minus a. This is the answer for f of a to b. But there is now for like all of these pairs, we cannot just do that. But this polynomial can be all pre-computed. And then for all of these pairs, what we want is just for all of these so you have some polynomial. So essentially this polynomial will be an array. And then we want to find for each of this here, I'll say how many. So I need some kind of, again, some FFT here on them, on these two things. Is this no, so again I need A and B are up to n. So I need the following. There's A, there's B, and there's like A1 times B1. No, we need this difference here. So A1 minus B1, A1 minus B2, yeah, essentially we want something like this, the absolute value of all of these. right? Is that correct? This, I think that is correct. Yeah, the polynomials can be done in logarithmic time. So n is in logarithmic time here. Log n, or something like that. I mean log n. This is not the problem. The problem now becomes how to compute this for every AB. So you have this polynomial which like you could compute, and now for all of these pairs, what about if I put all of these pairs in a frequency array? So in some like other polynomial, and I say, okay, instead of this minus, I will make all of these minuses here. Then I like multiply these two arrays, and then if I so this difference, we say this difference b minus a here, essentially saying like I don't care about, oh, I can't go outside. Well, that kind of changes the problem. There are m columns only. You can't just walk outside of them m columns. Okay, that changes the problem. That a lot changes the problem. You only need to compute up to m here. So I kind of think that like all I need to do, like when it fills up to m like that, and then it fills up the m columns, the m columns, and then this here from this point to the end point will cycle. It's like some kind of like not periodic cycling, but yeah, it's periodic, definitely some kind of mathematics you can pull off to achieve this. Then when you have this here, the end thing, and you have, but now the trick is like for each of the starting points here, you end up with a different ending. Yeah, that's a no, that's a bummer. It's not the same if you start here at the standard and here at the end, kind of. It's not the same. Here it will like feel like this, and then but if we do for each a, we cannot just yeah, this is heavy mathematics here. This is heavy combinatorics. And if it's not symmetric, it's kind of hard to compute it. Could be a way with like some inclusion-exclusion principle. This is a heavy duty problem. You want to know this polynomial because it's interesting, this here polynomial, but other than that, it's I think this problem is way difficult. So let me just refresh the standings. Let's see. Okay, so apparently not a lot of people solved G, so that's good. Interesting. Simple counting path with constraint repetitions. Permutation with arithmetic constraints. Presence, I know this how to solve. I don't know if there's some algorithm that like solves these permutations with there was something of this similar on AtCoder before. I would guess it was somewhere. There was some permutation problem that used with some similar constraints. So if I is equal to 1, it's derangements. Derangements are if I is equal to 1. Derivation by inclusion-exclusion. One main non-recursive formula for the number and set derangements. Any intersection of these particular there and I such collection yields. This says that we define Sk to be the set of permutations of n objects that fix the kth object. And this is like fix the ith object are n choose one where the ith object is times n minus 1 because this, and then you do this minus sum of the union of these, so where choose the ith and the jth, the intersection between these, and like fix two objects. And yeah, this is the inclusion-exclusion, but that's like on the n. So that's 2 to the n, this formula, and then like it gets down. And then what about our case? So our case is we can't fix one object, we can't fix our case is we want yeah, so this is this is like we define the derangement as all of the permutations minus these that fix objects. Okay, so in our case we want minus these that fix objects that minus these that fix any object, or minus these that fix objects on distance 1, or minus these that fix objects on distance 2. So like, okay, so we define some functions. So our answer is n factorial minus. So let's first define d1 as like derangements, what they have defined, but they have defined these sets that fix these objects as like D2 will be some set that has an object move to the left or to the right by 1. So these are like special derangements. And so forth, so forth. And then we want our answer is n factorial minus d sol. So minus exclusion, inclusion, exclusion on the d sets. This inclusion exclusion is 2 to the power of 5 or something, right? So this is not a problem, but if we have calculated all of these d's, this is not a problem. But how to calculate each individual d? So this is the arrangements that switch one element to like but these inclusion exclusions will have a set where it switches. Yeah, there is like set of 1, 2 where these are the union between these two sets is not actually like a union, but it's not actually just like a sum. It is defined as, it should be defined as like an special intersection function. There's a lot of mathematics going down into this problem. There's a lot of mathematics because I will just maybe explain all of the problems before the contest ends. There won't be a lot of people solved probably G fast. I'm not sure about G. Maybe I'm making it a little bit more complicated, but I think that there's some magic derangements here, inclusion exclusion, doing like, so you have like this formula, but then you arrive to some other formula, and then you do inclusions of both, and then you kind of it kind of gets more and more complicated. So I will start the explanations of the problems, even though the contest has not ended, so I can upload the video faster on YouTube. Okay, so yeah, let's close everything. Let's start. We're going to discuss only through F. And then after the contest ends, we will check the tutorial on G and EX. I believe EX is just like FFT problem, but really difficult to come up like with proper polynomials, and G will be some problem that has heavy combinatorics involved. And we need to upsolve them on some stream. So yeah, I like the problems. The first problem was pretty simple. We just had to say if two things are adjacent to each other, are adjacent horizontally, so not vertically as well. and you don't kind of need to create this to check. You just know that because this is in this order always, the adjacent things will have an absolute difference of 1. And then if this is the first thing here and the second thing is this, then it's invalid. And what I'm doing is essentially like if A is bigger than B, I'm going to swap, and I will say like A is always the element which is smaller. And it's okay only when, so only when A is equal to B minus 1, so one element shorter than B, and then A is not divisible by 3 because all of these are divisible by 3. That's one thing of writing this down. So A is not 3 or 6 or 9. So yeah, so this at the end, if it's okay, then it's yes, or otherwise no. B, what I did for B is just quite primitive, I would say, quite simple. I mean, maybe there are simpler solutions, but you were given this binary matrix and you needed to shift the rows which like are on the border by 1 to the counterclockwise or clockwise position. So these two here became here, and then this guy went here and this guy went here, and so on, so on. So like just like taking this and just shifting these rows. And what I did is just I created like a string, and I went like in clockwise, filled up the string. I then had this pointer which was like at the end of the string on the last character. So I start from there and then I go so one character over is shifted. If it's 0, it won't be shifted. And then this pointer, and then I go it through the same route, but what I do here is I just fill up this the same way. And SP++ means that, okay, first take P and then add plus when you're done with this operation. But at the end, I just module it with the s.size. S.size is just like, what is this, 4n minus 4 or something like that. And this module is just like just to come back over to 0 when you go over. And then you print all of these strings, so all of this matrix at the end. So it's pretty straightforward. Here I had this mistake of like overriding this to 0 here. It's you don't want to, because here you start from 0, here you want to end at 1, and here as well. Not n minus 1, but n minus 2, because the last element is included in this for loop. But all in all, just pretty straightforward. C is a binary search problem for the next 8 days. So if you want to just to quickly go over, so you have some pills when Takahashi starts taking them at day 1. And some pill is taken up to here, some pills taken up to here, some pill is taken up to here. All pills are taking some different amount of days. So this guy just went all on drugs. So that's on pills, and I mean, yeah, now it's just my video is going to be not demonetized, it's not even monetized, but like it's just because I said this word, YouTube is going to say, oh, what are you saying? Okay. Yeah, so it's pills. Yeah, that's so this ends up at some point in time. Every pill here is ended up, like he takes it up to here and then he stops taking the pill. And each day you take from this pill some amount. So like you take 20 of these, you take 10 of these, you take 5 of these, and so forth. Let's say here you take 100 of these or 25, and then doesn't matter. But what it matters is like so I know that in a sense of way, if I'm somewhere here, so if I'm on this day, on the ith day here, this is the ith day, I will take this amount of pills, and this is different from when I'm here. But because you can prove that when starting from here, and it will only end, it will only lower the amount of pills Takahashi will take until it becomes 0 at the end. This is monotonic function. So this function, it looks like something like this. So here, then lower, then lower, then lower, then lower, and then here it's like, oops, like something like that. So this monotonic function only lowers, and then if you have some monotonic function, you can binary search. It says like when is going to be the day that Takahashi reaches like some k pills, at k or less pills he takes. And then you want to binary search and then say, okay, here, no, this is too big, here, this is too small, here it's still too big, here it's still too small, and then when you reach here exactly at this day, you say, aha, okay, this would be fine. And this is exactly what we're doing, is just binary searching the function. L is not valid, R is valid in our case. The middle point we just take by summing up and dividing them. The pills we go through all of these n pills, and we say if the pill lasts till this m day, so it lasts more than the m days. That m is like the index we are searching at here. This is the index. If the pill lasts more than this, I will count that this day, this exact day, I will take AI dot second pill. So because this pill has like some amount of pills you need to take, so this substance has to be taken in some amount of pills. And then when these are counted, if they're smaller or equal than k, this means it's valid. So this means it's like on this side. And if it's valid, I want to try to get R, so R position up to this number, because I know that it's valid, but maybe there's something earlier than this point. That's why R is taken to M and L is taken to M in otherwise. But now R is now valid because this equation is valid, and the binary search will stop when the difference is smaller than 1. Smaller or equal than 1, and then thus we can prove that R will be a valid solution if here is a valid solution, and there will be one valid solution, even though maybe it will take a lot of days to come up with. Okay, that has been C. I think I explained it pretty well. The D problem was, so you were given like two connected components you were given, and then you want to add an edge between one and the other component such that you maximize the distance between one and this here, the maximum number. And what edge you should add such that such distance is maximized, i.e. What is the maximum distance that is maximum possible achievable distance. And essentially what I do is I just push BFS from 1 and from 7, and because they're different components, one of the BFS is going to like end in this component, and one of the BFS is going to end in this component. They are connected components, so I don't care. So essentially, because I push these BFSs, I find what is the maximum distance achievable by one BFS. So here from 1, this will be the distance 1, this will be a distance 1 as well. From 7, this will be distance 1, 2, 3. And then the answer is just like BFS from 0, BFS from the last number, so BFS from 1 here, BFS from 7. And whatever this maximum distance is, in this component, maximum distance in this component plus 1, because one edge I will add here, this new edge I will add here plus 1. And this is essentially it. So just a simple BFS. Nothing to write home about. E also was pretty simple. I will just skip it on like fast, because so what I did for E is essentially, so I have a tree, right? And then I note the depth of each component of each vertices. So this is depth 1, this is depth 0, 1, 2, 2, 2, 2, 2, 3, 3, 3, 3, 3, and then here let's say 4. And then what I'm actually doing is I'm saying at each of these I will have some maximum protection here. This maximum protection is in the inner array. So this is like this node protects maximum some nodes below. And let's say that this node has some protection of, let's say 2. This node, let's say, has protection of 0. This all other have protection of -1. So let's say this node here protects 1. This node protects 2 as well, and let's say like this. And now what I'm doing is I'm just pushing DFS from here, and I'm going down the tree, of course, as DFS does, but each time I visit a node, I kind of remember, I kind of increase this longest thing, and this longest thing here I have is just saying to what extent, to what depth in my subtree am I protecting. So this here, when it comes to this node, longest will be 2. And when it comes to here, longest will be 2, because 0 plus 2 is 2, right? So will be up to the depth of 2. But it comes to here, this node, and this longest now updates, saying that longest in my subtree will be 3, because I'm at depth 1, and plus 2, it's up to depth 3. And then it comes up to here, it says, okay, there's no updates, but still so this is protected. I'll say this is protected, this protected, this protected. Then it comes up to here, this protected, comes up to here, this protected, and now it comes up to 4, this depth is bigger than the longest, so this is not protected. Comes up to here, protected, and then comes back, and this is like protected, but this is maximized again. Now longest becomes, again, it's like back to 2, because up to depth 2. This here is 0, so it doesn't affect the longest. Then, I mean, the deepest, maybe deepest, not the longest, but I thought there's the longest chain from the root to some node. And then this is okay, this is okay. Then when it comes to here, longest is 2, it's not 3, then this is not okay, this is not okay, and then this is okay. And in this way we kind of do this algorithm. It's pretty straightforward. So DFS, just a simple DFS. Okay, so that's kind of cool. Now F to my, like, F is a known problem. It's if for those who want to know, hear more about this, it's called 3D coordinate domination. So a point x, y, z dominates another point x prime, y prime, z prime. I will talk about this in some other video in more detail probably. if for all of these holds this, that like x is smaller than x prime, y is smaller than y prime, and z smaller than z prime. And this guy comes up and proposes an algorithm to compute all sets of dominating points in n log n time. By using this method recursively, we can solve d-dimensional domination in n log d to the n d minus 2 log n. So this is like some kind of divide and conquer approach that he proposes. I haven't implemented this approach, but there's like a reference to this approach for those who want to know. It's already tested and stress tested, this thing here. So yeah, so this has been, this I used to, I stress tested because of something, but I don't know what, to be honest. But yes, this has a lot of history, especially in this like paper. I'm very curious about this divide and conquer algorithm. I once looked it up and I didn't quite understand, but I would probably look it up again and try to understand it. But what it does, it's first like sorts the points by x coordinate, and then every next point, if we can imagine all of these points, every next point, all of these points as like some, so you could imagine all of these points as some boxes. It doesn't like quite matter, but they are all sorted by x coordinates first, and that means that the next x coordinate, this next point has a bigger x coordinate than this, and what we want to achieve is there a point such that it dominates some other point fully here. We know that this point will dominate, so we know that they're sorted. Yeah, they're sorted the other way around. My mistake. They're sorted like this. So they're sorted like this by x coordinate. So I will talk about a little bit after that about shuffling the coordinates. Each coordinate, I actually will say that this is equal to like component, because these like can be thought of vectors. So like this guy here is some component, but okay, it doesn't really matter. What it matters is that because they are sorted, each next point is sorted by x. So this is smaller than whatever previous was. But now we want to take a look at something else, and this is like the y and z coordinates. And y and z coordinates are now all of a sudden shuffled. But there exists a cool technique, and it's called like convex Hall. It's not convex Hall optimizations, but it's something similar to convex Hall, convex Hall domination, or whatever you can call it. This frontier structure. This frontier structure for each. So here I actually rewrote now this as like x and y. So what I did is like, okay, I got rid of this x, right? And then I renamed y and z as like x and y. So now we only have points x and y that we know that we have to check domination between them. So we have to check the next, is this point what we are currently on, is there a point in our structure that dominates both on x and both on y, this point, because it already dominates on the first component, on this x, but does it dominate on the other components? This is what we want to check, right? This component, this x here, what was, we just remove it. It doesn't matter anymore. because we sort. Now to check this, does it dominate on x and y, what we do is we do some kind of frontier, and this frontier is just like, you can imagine it as like a graph of points. This x and y, like I will add on the x here, on some x, I will add some y here, right? And then here on some other x which is like bigger, if I add a bigger y, so I add a bigger y and a bigger x than this guy here, I know that this guy kind of is dominated by this guy here. So essentially this guy doesn't matter here. And essentially we can quite simply say, okay, the new guy x1 and x1 is bigger than y1, so it's bigger than x, and y1 is bigger than y. And this guy thus there no, actually, yeah, actually the other way around, I'm sorry. If I have x and y here, I need to, I will put here x1 and y1. And because we know that now this x here is smaller than the previous x, so x on this coordinate, and now this x here is smaller than this x, and this y is smaller than this y, it means that this point is kind of useless. So we can just remove that, and then we can say that this point dominates this point. But now you can imagine, okay, so we remove this. What about if a point has a bigger x but a smaller y? We must protect this. But what about if it has a bigger x and a bigger y? Then this point removes this point here. So this is removed. And essentially what it does, it creates some kind of convex hole here, which looks like this. And at the end, what we have is a graph which looks like this. If I add here, if between two x, so x1 and x2, if I add a bigger point here, I will remove to the left any points that are smaller than myself on x and on y direction until I come to this point which has a bigger y. So I kind of update the convex hole like this. I mean, it's not convex, but it's some kind of like frontier. It's called a frontier. Then let's say I add here a point. This point doesn't update the frontier because yeah, it actually, yeah, it does update the frontier because now the frontier looks like this. Yeah, because now if I come up with a point over here, let's say with some other color, if I come up with a point over here, this point will be deleted and this point will be deleted because they're both smaller. So I always delete everything in this range. And how is this possible? This is possible by using map. And the first component is x, the second component is y. The x components are what we are putting the points on, and the y components is what I'm visualizing here by this. And because of the sorted nature of map, i.e. that every x on the left will be bigger than x on the right, and in the map we make this convex hole, and this is like very well here says that maintains a data structure where x is mapped to maximum of y, so the maximum y seen with this x, while holding that for some other x that is bigger than this x, the y has to be small. This is what we said. for some other x2 that is bigger than x1, the y2 has to be smaller than y1, because y1 is somewhere here and y2 is somewhere there. So this is the main data structure, and update with other point, it just adds a point there. Okay, I went maybe too far into explanations, but it's just I want to explain it really well. So now here in F, the problem F, we kind of needed to just go over all of the permutations of this, because all of them can be kind of shuffled, and as soon as they're shuffled, this doesn't change anything, because there are strict inequality. So this is strict. So this is doesn't mean if they are equal, it just doesn't count it. So equality doesn't matter, but this is strict inequality. And I just permute the order. So I just have these three coordinates, vertices, and then I permute the order, and in A I all push all these points. There are 6 times n points, because for each n there is just 6 permutations, right? So 3 factorial. And yeah, that's kind of it for F. Yeah, so due to so the contest kind of finished. We want to see the tutorial on G. Okay, so it's dynamic programming. The number of ways to determine some of the terms P to satisfy this, the number of ways to among I to the I and j terms are predetermined. The set of integers okay, this is quite a complicated DP solution, but yeah, I kind of see this inclusion-exclusion, but I have to go over and prove this, like say for everything. Yeah, this case used for the inclusion-exclusion. Simple path counting problem. Okay, so for the DP we kind of know that like the transition can be represented with polynomials, that is the polynomial of the sum of some DPs. So he's just calculating the DP up to yeah, so this is the polynomial I'm talking about, the x minus 1, x to the minus 1 plus 1 plus x, where the exponent is considered with. Yeah, so this is what I came up with. The former DP is hard to represent as polynomials, since therefore it is sufficient to find f of n as this times that modulo so it modulo 2n plus 1 plus 2. So he's mirroring it. Okay, I kind of see when yeah, but this I will never consider having I have to look up this again, this method of mirror images, because it's okay. It doesn't matter. It's yeah. Again, as we said, fast Fourier transform on this polynomial. So I don't know f1 what it is, but okay, it doesn't quite matter. Thank you guys so much for watching, and yeah, check out my channel for other videos. I will be doing some other content as well, not just AtCoder and Codeforces things. Yeah, and subscribe. That's the main thing. Thank you guys so much for watching.